We just finished a little demonstration in which we saw standing waves set up in this elastic string as it went from a mechanical wave generator tied to the end of the desk. These standing waves were waves that appeared to be standing still. In reality, we know that waves were constantly traveling in one direction towards the desk leg, and they were reflecting off of the desk leg, inverted, and coming back towards where they started, interfering with the waves that were still being produced. There were waves going everywhere all the time in both directions, but they appeared to be standing still. They appeared to be standing still, however, only if they were at a very particular frequency. Okay, if I was sending waves down at one frequency and they were coming back at the same frequency, I may or may not get a standing wave produced. But if I chose a particular frequency at which I sent them down and they were coming back at, then I would get this standing wave produced. The frequency at which it occurs is what we call the resonant frequency. We talked about resonance earlier on in the simple harmonic motion portion of this unit. Resonance is that the property or that phenomenon whereby a disturbance can grow if I apply a force at the resonant frequency. The resonant frequency is the natural frequency of something at which it wants to vibrate. Everything has a natural frequency, including the string that I showed you the demonstration with. Everything has a resonant frequency, and standing waves occur at the resonant frequency or frequencies of whatever it is that you're sending the wave through. Standing wave might look something like this. You've got a waveform like this, but then you've got a waveform like this as well. I'm not suggesting here that the string that's forming the standing wave, or whatever it is that's forming the standing wave, is in two places at the same time, but it kind of looks like it's in two places at the same time. It's really going back and forth between the top and the bottom in all these positions. It looks like it's in both of those positions at the same time. Really, it's just happening so quickly that we can't see it going back and forth. Now, those are what we call antinodes. Antinodes are those areas of constructive interference. Versus these areas in the middle right here that we call nodes, 3 of them in the middle, then 1 at each end. These are the areas of destructive interference. If you put your finger on this antinode, then you're going to feel this string going back and forth. Even if you can't see it going back and forth, you feel it. Okay, if you put your finger on a node, then you feel almost nothing because there's complete destructive interference. The wave that's canceled out as a result of a crest always being there on one side and a trough always being there on the other side. Remember, this doesn't occur all the time, far from it. This occurs at a particular set of frequencies that we call the resonant frequencies, the natural frequencies at which it wants to vibrate. We can predict what those frequencies are. We can predict when it's going to start vibrating. Let's draw a few pictures here, okay? Let's first of all draw the first possible standing wave that we could get. If we have a string that's attached at both ends, then that first standing wave would look something like this. We would have an antinode in the middle, and we would have a node at both ends. That's the first standing wave that would be produced. If we turn up the frequency, then that standing wave is going to disappear. But if I turn it up a little bit more, then the standing wave will reappear, but this time it's going to have 2 antinodes and 3 nodes. Turn it up a little bit more, the standing wave disappears. Turn it up a little bit more, and the standing wave reappears again. But this time it reappears with 3 antinodes and 4 nodes. We could keep doing this. I'm not going to draw any more, but you can imagine that the next possibility would have 4 antinodes and 5 nodes, then 5 antinodes and 6 nodes, and so on and so on and so on. What we want to do right now is use these diagrams to predict what the frequency at which this will occur is. In other words, we want to find the resonant frequencies of this string. If this is a guitar string and we pluck it, what's the frequency of the sound that we're going to hear? Basically, that's the question we're asking right now. So here's what I want to do. I want to label, first of all, the length of the string as L. In all 3 diagrams, the length of the string is L. Then I want to define the length of the string in terms of a wavelength. Over here, I'm going to draw a complete wave. In fact, I'm going to draw a couple complete waves. How much of a wave do we have right here in the first diagram? How much of a wave do we have here in the first diagram? Okay, let's go over here. I want you to tell me when to stop. Okay, I'm starting right here, which is at an equilibrium, going through a crest back to the equilibrium. I'm going to do that right here, and then I want you to tell me how much of a wave I have. Right there, right? How much of a wave is that? Is that a full wave? Is that a half a wave? Is that a quarter of a wave? 3/4? That's a half a wave. So I'm going to say L is 1/2 of a wave in that case, or 1/2 of a wavelength. What about the next one? Okay, we start right here. We keep going this time to here. How much of a wave is that? That's an easy one, right? Stefan, how much of a wave is that? That's a full wave. So we're going to say L is equal to lambda there. Let's do the next one. We start right here. We keep going, we keep going, we keep going, and we're back to here. How much of a wave is that? Where is it? That's 1.5. We're actually going to call it 3/2. And you're going to see why we're going to call it 3/2 in a few minutes. If you call it 1.5, that's okay, but it's easier to see a pattern if we call it 3/2. All right, so let's rearrange each of these now. We've got L is equal to 1/2 of a wave, L is equal to a wave, L is equal to 3/2 of a wave. Let's rearrange each of them to solve for lambda. This becomes 2L. This just becomes L, of course. And this lambda becomes 2/3 L. And now what I want to do is use the wave equation that we learned on the first day of the wave section of this unit, which is V is equal to F times lambda. If we rearrange that, we get V over lambda, right? The wave equation says F is equal to V over lambda. And I want to do some substitutions right now. V is V, but lambda is 2L. So I'm going to say F is equal to V over 2L. The first frequency that would be produced when you pluck a guitar string is equal to the speed of the wave in the string divided by 2 times the length of the string. That's the first resonant frequency, the first standing wave that will be set up in that guitar string. The next one, we're going to say F is equal to, well, we just replace lambda with L. F is equal to V over L. And the next one, we'd say F is equal to V over lambda, which is V over 2/3 L. I'm just going to simplify that a little bit. When I do, I get F is equal to 3V over 2L. There's a pattern formed here. Does anybody see it? V over 2L. The second one is V over L, but isn't V over L the same thing as saying 2V over 2L? Isn't that the same thing? V over 2L, 2V over 2L, and 3V over 2L. In other words, if we call this the first harmonic, the second one would be twice the first one. And the third harmonic would be 3 times the first harmonic. Does that make sense? That's why the first standing wave that you saw on that string that I showed you here had a frequency of about 4.5 hertz. What was the second one? About 9 hertz, about twice the value of the first one. The third one, about 13.5 or 14, 3 times the value of the first one, and so on and so on and so on. Okay, when you pluck a guitar string, you're going to get a few different harmonics set up in that guitar string. Okay, hit a piano string, blow into a tuba or a trombone or whatever the case may be, a flute or whatever the case may be, and you're going to get multiple standing waves set up. They will correspond to the harmonics of these, of the resonant frequencies here. Does that make a little bit of sense? All right. What do you think is going to happen? Actually, let's do an example, and then we'll talk about what I was going to ask you next here. Unfortunately, one that's not in your book here. says a 25 centimeter long string is set in vibration and the speed of the wave through the string is 500 meters per second. What are the first three possibilities for harmonics in the string? Let's draw a picture for this, okay? Let's draw a picture. We have our string right here that goes looks something like this. This would be the first harmonic, right? The first standing wave that's set up. This would be the length of it. And we're going to say the length of this is a half of a wave. And therefore, lambda is equal to 2 times L. We're going to say F is equal to V over lambda, which says that if we do a substitution there, V over 2 times L. So the frequency of the first harmonic would be V over 2 times L. Let's find the value of that now. The speed of the wave is 500 meters per second. The length of the wave is 25 centimeters. We're going to convert that to meters. So we're going to say it's 2 times 0.25 meters. 500 meters per second divided by 0.5 gives me 1,000 hertz, which we should actually round to 1.0 times 10 to the 3 hertz. Now, watch carefully what I'm about to do. We want to find the frequency of the next harmonic that's produced. We have a couple of options. We could go back to this diagram, redraw this diagram, derive the equation for the second harmonic, solve it like we did the first one, then go back and draw the third harmonic, derive the equation for the third harmonic, solve it, or, hold on one second, and then we'll let you go, or what could we do if we wanted to find the value of the second harmonic? We know that it's twice the value of the first harmonic. So the second one is going to be 2.0 times 10 to the 3. What's the third one going to be? 3 times the value of the first harmonic. Don't worry about deriving equations for all of them or remembering equations for all of them. If you have the first one, that's all you got to be able to do because the second one is simply going to be twice the value of the first one. Does that make sense? All right. Have a good weekend, everyone.